Hi, so today we'll be discussing the paper Natural TTS Synthesis by Conditioning WaveNet on Mel Spectrogram Predictions by folks from Google and UC Berkeley. Yep, the title is totally a mouthful. So instead, we'll just call it Tacotron2, like everyone else. So the problem is about text-to-speech synthesis. So given a text, you want to predict some speech. So say given this paper describes Tacotron2, the text of this, you want to basically replicate my voice or anyone else's voice saying this same sentence, right? So they say that the system is composed of a sequence-to-sequence prediction network that maps character embeddings to mel spectrograms, followed by a modified WaveNet model using a vocoder to synthesize time domain waveforms on the spectrograms. That is definitely a mouthful. So we'll break it down. So what happens is, so you have a text, you have text. Say I am Jack, and you have to predict audio or speech in this case. But speech is in the end just audio. So first question is how do you represent audio? Like what is represent or what is even audio? So audio is a wave which is which varies in time or which goes through in time and varies in pressure. So audio is a wave of pressure. So at different time you have different pressure and that constitutes your audio. That is what you have in .wav files. You have the pressure at each point in some particular value, and yeah, this is your audio and wave files. So what they do is, what we have to do is, given this text, you have to predict this wave files which are in the time domain. So as they say here, time domain waveforms. So because this is in the time domain, and you call this time domain waveforms, right? So what are character embeddings and mel-scale spectrograms? So character embeddings. So how do we process text? We process text character by character, IAM space JACK, and each of these characters is given a embedding through some embedding layer. So that is the character embeddings. What are spectrograms? We'll come into that later, but you can just think that a spectrogram is a way to represent another way to represent an audio. So you can take this wave file and create this wave and create a spectrogram out of it. We'll come into that later. They describe it in detail later. But what they do essentially is from this text, they produce a spectrogram. This is your spectrogram. And from this spectrogram, they predict this wave file. And this part is called a vocoder. And this is just your feature extractor of sorts. So as I say, they use a sequence-to-sequence model, feature prediction network, that maps character to mel-scale spectrograms. So a feature extractor which maps your text in the form of character embeddings to your spectrograms. Actually, it is mel spectrograms. We'll talk about what mel spectrograms and spectrograms are later, and then you have a modified WaveNet model acting as a vocoder to synthesize time domain waveforms from the spectrograms. So you have a vocoder, which is in this case a modified WaveNet, which is a previous approach, which takes the spectrogram and predicts the audio or the wave from it, the time domain wave. So yeah. They say that their model achieves a mean opinion score of 4.53 compared to a MOS of 4.58 for professionally recorded speech. What is MOS? MOS is just asking humans to rate your audio sample from 1 to 5 and taking the mean of it across samples and humans. Right. And they say that uh, so what previous approaches did was uh, they did not have this. They did not have spectrogram. So specifically WaveNet, which is this thing here, which is a vocoder. It was a generative model of the time domain waveform, which had a good audio quality, generation quality, but the inputs to the WaveNet itself were complicated. So the inputs were some linguistic features, phoneme durations, and fundamental frequency inputs, which required a lot of handcrafting to do. And so this vocoder, which produces the wave, in the original WaveNet paper, that did not take spectrograms as input. It has some very complicated features as input, and that was not very feasible always. right? So instead, in this paper, they predict the mel spectrograms and give that to the vocoder instead. Uh, Also, this is called the Tacotron 2. So there was already obviously a Tacotron 1 in which they had this part. They had this part. They had this part. They took the text and predicted the spectrograms from it, but they did not have this part. They did not have specifically, they did not have WaveNet. Uh, they had a vocoder, but they had this Griffin limb algorithm as the vocoder, which was not a neural approach. It was actually a signal processing based heuristic, like deterministic or some, not deterministic, it is a signal processing algorithm. There was no learning involved in it. And as they say, it was simply a placeholder for future neural vocoder approaches because it had some artifacts and lower audio quality. So well, tada, this paper. So this Tacotron 1 did not have the WaveNet vocoder, and the WaveNet paper did not have the spectrograms. So in this paper, they have both of them. They have the spectrograms and they have the WaveNet-based vocoder, right? And they also say that the spectrograms are a compact representation, which allows their model to have a significant reduction in size compared to the WaveNet. So what they mean is that this spectrogram is a compact representation, its dimension is less, it is compact, so you don't need a lot of parameters in the WaveNet to uh, predict the wave from it. If it was a bigger, like less compact representation, you might need a lot of parameters here, but since it is a very compact representation, it has all the information in a compact form. You don't need such a big model here. So they were able to reduce the size of the vocoder as well. So yeah, that's all for the overview. Let's dive deeper into the architecture. Okay, so now let's talk about MEL spectrograms. So first, for MEL spectrograms, we need to know what a Fourier transform is. I barely know anything about these things, so I'll just try to explain the best I can. So say you have a wave. You have a wave, any wave. It is a function of time, something like x is varying over time, you have a wave. Now, what a Fourier transform says is that you can represent this wave as it's an arbitrary wave. You can represent this wave as a sum of different, different, different waves. Each wave is simply a sine wave. Let's make this wave more complex because otherwise both of them look like sine wave. Maybe it is some random, I don't know, arbitrary wave. This is definitely not a wave because this is not a function at this point, but who cares? So what the Fourier transform says is that you can take this wave and represent it as a sum of different waves, different, say, very simple waves. So if it is y, or not y, let's call this y only. Y equals to f of t, which is some very complicated function. You can instead represent this as a combination of some wait times a very simple wave called of the form sine of omega I ai t plus phi I. So basically you can represent an arbitrary complex function or an arbitrary complex wave as a sum of constituent simpler sinusoidal waves with different frequencies, amplitudes, and phase. So first of all, for the basic sine thingy, uh, okay, why did it disappear? Again, why is this disappearing? Okay, interesting. I think I discovered a bug in OneNote. Let me try a different color. Yeah. Anyway, so if this is a wave, then omega represents to the frequency or how much time it takes for one period to complete. What is the time duration between these two? So higher omega. Never mind. I don't know what higher omega leads to, what lower omega. I always mess them up. Basically, if it is a high frequency, just time duration would be short, and you would have a wave which is something like ta 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 ta, right? Yeah. and the amplitude represents this, what is the uh, maximum that it goes, and the phase represents how much shifted it is. So this is a sine wave with phase 0, and this is a sine wave with some initial phase. So yeah, phase tells you how much shifted you are from the origin. So you have your phase, you have your omega, and you have your amplitude. So these are the three parameters which define a very simple sinusoidal wave. Don't worry about cosine, because if phi is 90, then this would be a cosine. So I mean, phase can adjust for sine, cosine, whatever. So yeah, this is what the Fourier transform says, that you can represent a complex function, arbitrarily complex function, as a component of very simple functions, sinusoidal functions. Now, this I can actually go from 1 to infinity, because the better you want to approximate it, the more components, subcomponents you would want to have, and it is in the limiting case, you need infinite components, right? So this is, but what do you get from a Fourier transform? You get sort of a frequency representation. So you initially had a uh, time function. Now you have a frequency function. Your wave is a function of frequencies, right? You basically get like what frequencies this wave consists of, and especially in the case of audio, what frequencies does this entire wave contains of. But this is very global. This tells you in the entirety of the time what frequencies does it contain, or which does not really sound that interesting, because like, why do I care? Like, it's such a big wave. Do you really want to know what frequencies it consists of on a very global level? Maybe you do, but not necessarily. What you can instead do is, uh, if you have a wave, you can chunk it. Like, you can get a chunk, apply a Fourier transform here, then have another chunk, apply a Fourier transform here, and just keep on doing that. And in each chunk, you'll get you'll get these things. You'll get these things, and more importantly, you will get the amplitude for each omega. So at each point, you'll get something like what is the amplitude for your different omegas, what is the amplitude. You'll get a value for all of them, right? So if you apply Fourier transform to a small chunk or a short sample, you'll get the amplitude for the different omegas at that for that window. Now, if you slide along that window, so you apply this here, then you apply this here, then you apply this here, then you apply this here, you'll start getting different amplitudes for these frequencies over time, and what you'll get in the end is something like this. So you will have, at each point you will get for that window what was the amplitudes of the different frequencies. So how much of the what was the magnitude of each frequency present for that window, and as you slide along that window, that will give you a time picture. So at so this is what a mel spectrogram is. So it gives you a time representation of how the frequencies vary. So uh, do they have a mel spectrogram picture here? They do, but it is very pixelated. But yeah, what it essentially is, oh no, it is not pixelated. Yeah, so you have the frame, which is essentially time. So, which is the window, actually, the window. And for each window, you have, these are the frequencies. The y-axis is the frequency, and the color represents the amplitude. So you get sort of a visual representation of the image, which tells you at each point that for that particular frame, at that frequency, what was the amplitude. So this sort of allows you to represent the audio as a image of sorts. And this uh, is called the short time Fourier transform. So yeah, this is called a short time Fourier transform, this particular thing which I mentioned. You apply Fourier transforms to short time durations. Now a MEL spectrogram, so you get a what you get out of it. This thing is a linear spectrogram. Technically, it's a linear spectrogram. But in MEL spectrograms, you apply some transformation over this. Uh, you apply some nonlinear transformation of this to get this MEL spectrogram. You can basically think that you apply some convolutions to it. It is actually sort of like that. You just apply a convolution filter over top of this to get this MEL spectrogram. And this is a specially defined convolution filter which corresponds to how humans perceive uh, audio, and it basically clubs together a few frequencies which we perceive based on how we perceive. So you can read it here. A MEL spectrogram is related to the linear spectrogram. It is obtained by applying a nonlinear transform to the frequency axis of the STFT and summarizes the frequency content with fewer dimensions inspired by human auditory systems. So what effect it does have is that it emphasizes the details in the lower frequencies, which are critical to speech, while de-emphasizing the high frequency details, which are dominated by noises and other things, and which need not to be modeled that well. So basically, you have this and you apply some filter on top of this to bucketize a few of these frequency dimensions in such a way that it corresponds more to how we humans perceive speech, and it also makes it more compact. So since you are bucketizing a few of them, it allows for a more compact representation. One tiny problem, or I don't know if it's a bug or a feature, about MEL spectrograms is that they do not have phase information. So this small thing called phase, which got ignored here, is ignored. I mean, MEL spectrograms don't have phase information in them. They say that this is actually a feature because since they are invariant to phase, they are smoother than waveform samples and easier to train using squared error loss. And here they talk about it a little bit more, that while spectrograms discard phase information, algorithms such as Griffin-Lim are capable of estimating this. Uh, so it is actually a lossy transformation. So a MEL spectrogram is not a complete representation of an audio. If you take audio and compute its spectrogram, you are losing phase information. So you're discarding the phase. So you can't go back directly. But if you had the phase, so if say somehow you had the spectrogram and the phase, you can actually directly, it is trivial to get the wave back because you can use something called the inverse Fourier transform, which can take the phase and the spectrogram and predict the audio like deterministically, right? So it would be a trivial problem, but we don't have the space. That is the problem. The Griffin-Lim algorithm tries to estimate the phase, but obviously it doesn't work that well, Amisha, always. So yeah, they say that MEL spectrograms discard a lot of information. I mean, they also have that convolutional thing going on. So they are even a more compact representation than the frequency spectrogram, linear spectrogram, because of this MEL transformation. So they have even less information. So it should be technically harder to predict the wave from it. But they say that uh, since it is a simpler representation, a neural network might be able to work with it better to predict the audio. So while it lacks the information, but since it has a compact and a simpler representation, the neural network can utilize it better to do the heavy lifting and like figure out the phase internally somehow and predict the audio. So that is their reason for using a MEL spectrogram, right? Okay. So now let's talk about the architecture. They go very deep into the architecture details, which is good. So here they talk about the spectrogram calculation details. So some technical details which we don't want to waste time on, other than if you're implementing this. uh, so yeah, some of the things. Yeah, they do use log compression on their MEL spectrograms, which helps them. I mean, usually log transformation helps for numerical stability or whatever. So their network is composed of an encoder and decoder with attention. So the encoder converts the character sequence into a hidden feature representation, which the decoder consumes to predict a spectrogram. This is a typical sequence to sequence thing where you have a text, say, or a sequence. So I like bananas, which I do, even though I'm spelling them wrong. So this is an input sequence, 1, 2, 3, and say you want to translate it to some other language, say Hindi. मुझे it's been a while since I wrote Hindi. मुझे केले पसंद है. Don't worry if you don't get Hindi. Neither do I sometimes. So this is another sequence, 1, 2, 3, 4. 1, 2, 3, 4. So you took a sequence and predicted a sequence. Right. What they usually do is you have a encoder model which will take this, create a feature, some feature. So there's a model which takes this, creates a feature, and then so this is the encoder, this is your feature, and then you have a decoder model, your decoder which will predict this. This is your decoder. Now you usually have attention here everywhere, wherever, because well, attention is good. I won't call it attention now. It's 2024 now. So yeah, we have attention everywhere here, wherever you can fit it. Right. So in our case also we have a sequence to sequence prediction because you have what is the sequence? So you have the text in which is characters, a sequence of characters in this case, and your prediction is mel spectrogram, which is actually also a sequence because you have the prediction for each frame, as you can see here. So you have frames. So each frame is a constituent of that sequence. So it is a sequence to sequence model with a lot of very weird architectural details, which we can actually skip, but because nobody, I don't think, uses them, they use transformers now, but whatever. Let's pay respect to our elders or the previous papers. Right, so the input characters are represented using 512 dimension embeddings, which are passed through convolutional layers, followed by batch norm, ReLU, blah blah blah, again blah blah blah. So they have a LSTM layer on top of it. Like who uses LSTM now? But yeah, they used it by LSTM actually. So as you can see here, you have input text, character embeddings, some convolutions, and some by LSTM layer, and some attention on top of it. Right. So this is your encoder. And this encoder output is consumed by an attention network, which summarizes the full encoded sequence as a fixed length context vector. This is just typical attention. They have a locality sensitive attention, which I'll skip because other papers in the future discard it. Right. And they have a decoder, which is an autoregressive RN recurrent network. So this is the decoder, which is again, as you can see, a LSTM. And it has two parts. It has a pre-net and a post-net. Right. Here's my pointer. Yeah, this is the pre-net. So while training these autoregressive models, what you usually do is you do teacher forcing. So it is easier if I just say it in the context of text. I like bananas, right? And you predict. So when you're doing training, you don't predict the entire thing once. You first predict the first word, say mujhe. This is the first thing you predict. Then you feed this back to your model, and then you feed this back to your model, and then you predict the second word, kele, and then you predict that again. You feed that to the network and again predict this. So it is a step-by-step process in which you feed the model, the decoder, the previous input, right? During inference, you feed what the model predicted, but during training, you do teacher forcing. So like regardless of whatever was predicted, even instead of mujhe, if it predicted tumhe, uh, since the ground truth was mujhe, you would feed this while training because you have access to the ground truth. You feed this while training. This is called teacher forcing. This is how these networks are trained. During inference, you if it predicted tumhe, you will have to predict tumhe only because you did not have this ground truth. So anyway, this is how it is there. And the prenet is basically to process this. So in this case, we have a mel spectrogram. So the prenet just processes the mel spectrogram, and they said that it is essential for that. And then they have some LSTM layers on top of it, and with the LSTM layers, they use a linear projection to predict the spectrogram at that point, at that for that particular frame. Also, they have a postnet, which is interesting, uh, which I found very interesting, or maybe not so, but I found it interesting. So after you're done with the entire prediction, right? So after they are done with the entire prediction, what they do is that they pass the whole prediction, this whole predicted spectrogram, through another convolutional layer, which predicts a residual on top of this. So the postnet takes the predicted spectrogram from the decoder and predicts a residual on top of it, which is added to the prediction from the prenet to get the final output. What this does is that it gives it a sense of global editing, right? So again, it is easier to explain in the form of text. So during prediction, you are predicting it one at a time. So you are predicting, okay, let's switch from Hindi, but say since you're predicting a very long sentence like quick brown fox jumped over the lazy dog. I don't know why I always refer to this, but yeah, this is my sample sentence. What during the prenet, you have to predict it one at a time, right? And while you're predicting this jump, you only have information about the past. You don't know what came in the future, right? So it would be good if you had the future information. So what they say is that what to do is that okay, we'll first have a prenet which will do this. Then we'll have a postnet which will take the entire thing and make some edits. So say you predicted under here, which seemed fine while you were predicting one by one, but when you look at the overall sentence, you see like, okay, this should actually be over. So this gives you access to some global context, and it also enables you to access the future for this prediction. While inference, like without the postnet, you only had access to the past, but because of this, you also have access to the future. Also, obviously, this is after the future has been predicted. This is like after the prediction has been done, then only you get access to the future. But yeah, this allows you to make some global edits, like some edits based on the global structure, which can be useful. So, say if you have an audio uh, based, you might want to make some edits locally based on how the audio sounds on a global scale. So that is why they have the postnet, which they also confirm that helps them a lot. Right, that is the postnet, and they use MSE for this. Uh, yeah, and they also have this stop prediction. So when do you know that you have to stop predicting? So in text, you usually have a whenever you predict a end of sentence token, but in this case, they have a separate network, small linear network, which predicts a stop token. So at any point, if this stop token is predicted with a very high probability, you stop producing your mel spectrogram, and that is the length. Now this is a problem sometimes because if this is not predicted, then you will keep on generating your audio. So say you have to generate it. So like say for the text you inputted, the typical audio would be like around 20 seconds. But since there was some problem with this uh, stop token or the threshold, it is not being predicted to stop, and you might generate like 120 seconds or 100 seconds of video, and there might be a lot of repeating happening in that case, and you will get a garbage output. So this needs to be tuned properly in this case, right? And then yeah, they have some regularization and sit on top of it. So this is the spectrogram prediction. Then we have the WaveNet, which takes the spectrogram and produces the waveform. So next we have the WaveNet vocoder. So what the WaveNet does is that it takes this mel spectrogram and it predicts the wave from it, hence the WaveNet. So the main innovation of the WaveNet paper was, the main problem was actually that audio is very long. So treating audio as a sequence is very long because audio is sampled at something like 24 kilohertz. So which means that in each second, 1 second, you'll have 24K points, data points to predict. So if you have a, say, a 10-second audio to predict, you will be predicting 240K tokens, which is huge if you consider text, right? So yeah, audio is a very big sequence, and thus you need very big receptive fields to predict it. So a receptive field is how much at a particular point, how much data are you referring to? So in this case, a receptive field, like at this prediction point, how much of it is you are referring to? Are you referring to like 3 of them, or are you referring to 5 of them, or are you referring to 7 of them? It is more common in images, so it is easier to explain in images. So if this is a very it's image at a particular point, what how many pixels are you attending to? So if your receptive field is 1, you might be just attending to 1 pixel. If your receptive field is a 3, at this particular point, you might be attending to like a bigger chunk, 3 pixels around that point. So since you have to predict very large sequences, right, you will need to have a higher receptive field somehow so that you can access more information, like a larger sequence at each point. Now, a way to increase the receptive field is just stacking more layers. So if you have, say for images, if you keep on adding more and more and more convolution networks, eventually your receptive field will increase because at each point a receptive field increases. You can think about it, but say for example, there are better diagrams than I can probably make in the internet, but let me try. So if you have a 3 by 3 convolution at this particular point for this pixel, or maybe a 2 by 2 would work. So at this point, you would be just referencing, say this, sorry, 3 by 3. So you would be at this pixel, you will be referencing this subset, right? This is what you'll be referencing at this pixel. But at the next convolution point, so you'll be referencing these of them, all these. And this particular one here would be sort of referencing this. So in effect, when you are doing a convolution here and considering all of them, like this is conv 1, and when in conv 2, you're considering all of them, so you would actually be considering a bigger circle. Since you will also get the receptive field of this. So the receptive field would increase. So one way to increase the receptive field is just by like adding a lot more convolution layers, but this would quickly be problematic from a performance point of view. What you do instead is use something called dilated convolutions to quickly increase your receptive field without like having a lot of compute added to it. And what dilated convolution does is that it skips things. So now let me go 1D because it is easier to explain in 1D, but say you have x1, x2, x3, x4, x5, x6, 7, 8, 9, and 10. In a normal convolution at this point, say a 3 by 3 convolution, you have this, right? Let me go in the middle. It is easier to explain it in the middle. Yeah, here you have this in a normal convolution. In a dilated convolution of 3, I might be wrong, but what you would do, I might be wrong about the exact specifics. What you will do is that you will skip some intermediate parts. So you'll probably skip this too. You won't take this. you'll take this, skip one. So you'll skip some intermediate steps and access the other one. So you are basically expanding your or dilating your receptive field by skipping some intermediate ones. So with the same number of layers, you'll get a bigger receptive field because you are skipping a bit of them. So as you can see, this made the receptive field feel like 5, even though it was like a 3 by 3 convolution. So this is dilated convolutions. So the WaveNet had a lot of these dilated convolutions. That was the main thing there. Apart from a few architectural changes, it had residual connections, skip connections, some different activation, and all those things. But that was the main thing behind the WaveNet, so, dilated convolutions. And this is what they say, that they have a modified version of the WaveNet to invert the melts into the time domain. There are 30 dilated convolution layers grouped into cycles, blah, blah, blah. You don't need to worry about that. To work with this, so yeah, also one other thing is that the melt spectrograms are predicted on a frame level. So if you remember from our short time Fourier transform thing, you take a frame, you take a window, and for each window you get a particular short time Fourier transform. But now you have to predict this entire audio signal, right? So there is a mismatch in the sequence, the length of the sequence, because assuming, so usually these windows have an overlap, right? But assuming they don't have an overlap, which would be very bad, you won't want to do that. But say you have a 20-second video, and that will have a lot of, like, as you saw there, that it would be something around 480K samples, right? uh you need to basically you need to upsample your mill this input a bit to match the uh, time scale of your predictions. Also, as the output layer, they don't have a softmax, so audio is stored in 16-bit, I think. So so at each point you have a 16-bit number which you are trying to predict in the audio, which is like 2 to the power 16 possible values. So one way of doing of predicting it is to have a softmax on top of it. Not obviously 2 to the power 16, but what they do is they discretize it into 256 particular values, and they have a softmax over 256, right? That is one way of doing it. At each point you have a softmax over these 256 values. But what they do instead is that they use a mixture of logistic distributions, so which is essentially just multiple logistic distributions. So at each point you are predicting the output y to be a weighted combination of some logistic distribution, right? This is some logistic distribution. And logistic distribution is a particular type of distribution, not like a Gaussian, sort of like a Gaussian, different from a Gaussian. So at each point you're predicting the output as a mixture of logistic distributions, and you predict you basically predict its parameters, the weight of each logistic distribution and the parameters of the logistic distribution, namely its mean and variance. So at each point you predict the mean, the variance of this logistic distribution, and the probability that each logistic distribution is picked. It is not actually sigma, it's actually more like which one of these is predicted. So say if you have 3 logistic distributions, uh, you first choose one of these with some probability which is given by this. So you also predict this probability, and then you just sample from this. And for that you need the mean and variance. So this is what they use as the output layer instead of the softmax. It probably works better. Yeah. And they use the negative log likelihood loss for it because you have this whole distribution and you can calculate what the probability of the ground truth was, and from that you can calculate the log likelihood, negative log likelihood, and use that as a loss. So yeah, that is mostly the architecture. Most of it is not being used right now in the latest approaches, but it was one of the revolutionary things at that time. So now looking at the experiments and results. So they train the model in 2 steps. They first train the mel spectrogram predictor and then the vocoder. So Going back to our diagram somewhere. Yeah, they first train this part, which takes the text and predicts the spectrogram, and then they train the WaveNet, which has the spectrogram and predicts the wave. Most importantly, they while they use the ground truth for this, they use the ground truth spectrograms for this. They don't use the ground truth here. Oh, I mean, they don't use the ground truth spectrograms here. Like the data set is in the form of text and audio. From the audio, so GT text and GT audio, and from the GT audio you can extract the GT melts from the short time Fourier transform. So while training the feature extractor, they use these melts, GT melts, but while training the vocoder, they don't use the uh, GT melts. This is not GT. So this is so while training the vocoder, which takes the spectrogram detects the waves, they use the GT audio, but they don't use the corresponding GT melts. They instead use the melts predicted from the spectrogram, and they say this helps them better. Later, they'll say this later, but that helps them supposedly. Right, and they talk about teacher forcing, which I already mentioned. Right. Although, yeah, one small thing is that this, while doing this, this feature extractor is run via teacher forcing. So at each point you feed the melts from the ground truth and not from the predicted spectrogram. So this spectrogram predictor is run using teacher forcing, and the output from that is used as input to the WaveNet while training. During inference, this won't be run in teacher forcing. None of this would be run in teacher forcing, basically. Right. So yeah, then some other details. Then for evaluation, they have MOS, which I already mentioned, which is just asking humans to rate it from 1 to 5. And obviously their approach works the best. The ground truth is 4.58, their approach is 4.52. WaveNet is less, Tacotron is even less, and these are some old approaches, parametric and concatenative. So yeah, their approaches works the best. And yeah, then they have some error analysis. So uh, their errors consisted of 0 repeated words, 6 mispronunciations, 1 skipped words, and 23 had unnatural prosody. So prosody is the characteristic of a particular person. So each of us has a particular pitch or the way we speak. Prosody is like how would you distinguish different speakers from each other, is what my understanding is. It gives the audio its flavor. So yeah, they have some problems in modeling the prosody, which makes sense because they only have the text as input. So since a particular text can lead to multiple possible audios, it is naturally a one-to-many problem, and yeah, that is why they've suck in prosody a bit. They also uh, test generalization by using text from a different domain, basically. So they train on some particular domain, and then they text, then they train on, and then they try to test on news headlines, and they receive a slightly worse score. And interestingly, it performs worse than WaveNet. Not worse, but almost. So the gap between WaveNet and their approach is not a lot on this news data set. And so there is some generalization issue. So they say that, so the examination of the human judges says that their neural system generates speech that is more natural and human-like, but it can sometimes run into pronunciation difficulties while handling names. So basically, if you they say that their model is able to generalize the feel of the audio, so their audio still feels natural, but because they are generalizing to a new domain, the pronunciation, some particular pronunciations get messed up. Then they have the ablation study. So this talks about the whether or not to use the predicted or the ground truth spectrograms as input to the WaveNet. So they say that as expected, the best performance is obtained when features used for training match those used for inference. What they mean is that both during inference and training, we use the predicted spectrograms as input to the WaveNet. However, one particular case performs really bad when what you do is that so this is your text, this is your mel, this is the feature extractor, and then you have your WaveNet and you have your wave. So one particularly bad case is that while training this, you use the ground truth, and while inference, you use the prediction. So this is if inference this, and if training this is worse. This is very bad. This is this particular case where during training use ground truth and during inference use predicted, because if you train the vocoder wavenet to use the ground truth while training, if you show it the ground truth while training, if you suddenly switch to your predictions, then there would be a distribution shift, and that would mess things up, basically. So, however, when trained on ground truth and made to synthesize from predicted, the result is worse. This is because of the tendency of predicted spectrograms to be over smooth and less detailed, and basically a distribution shift in some sense. Interestingly, the reverse doesn't hold true that much. So if you train on the predicted and use the ground truth, that is not that bad. Maybe because the ground truth is overall fine in some sense. So showing the model some high quality data like the ground truth during training and then showing it a crappy predicted thing might be worse than like showing it a crappy thing during training, which is the predicted one, and then showing it a better data during the prediction. So maybe that is why this is not that worse. Yeah. Also, here they say that instead of predicting mel spectrograms, they could have simply predicted the linear spectrograms. And if they predicted the linear spectrograms, they could have used the Griffin limb as well. But Griffin limb performs worse. Basically, you don't want to use Griffin limb because it has a very low score. But if you had a wavenet on top of the linear spectrograms instead of the mel, it performed more or less worse. So mel is not that needed in this from this table. But what they say is that since mel is more compact, it is better because mel is a more compact representation than linear. It is smaller. So mel is 80 dimensional, whereas linear is 1025 dimensional. So a more compact representation is better in general because it also makes it smaller and also it probably is a better representation. Then the post-processing network is important in their ablation. They say that the post-processing network is important because, as I mentioned before, it allows you to access the future in some sense. Here they talk about simplifying the WaveNet. So they say that a defining feature of WaveNet is the use of dilated convolution networks to increase the receptive field. They say that because MELS is a more compact representation, you might get away with a shallower network because they are a much closer representation of the waveform than linguistic features and already capture long-term dependencies across frames. So basically, since it is a more compact and better representation, you can get away with a smaller network. This is what they show in this particular table, that even with smaller networks, you get a good enough number. So if this is the score with 30 layers, 3 cycles 10, and if you reduce it a bit, then also you get a decent result. And if you reduce it further, then also get a decent enough result. But yeah, you can't totally get away with dilation. If you use a dilation of 1, which is like not using any dilation, you don't get such a good result. So they say that a large receptive field is not essential factor for audio quality. However, we hypothesize that this is due to the MEL spectrograms. Basically, the MELs allow them to reduce the receptive field a lot because they are a much better compact representation. But you can't totally get away with it unless you want such a score. So yeah, overall, that was the paper. That was it. That was the Tacotron2 paper. It was a foundational work and a lot of things were built on top of it. It has a good NVIDIA's implementation also, which you can look out, which I was looking out recently. Yeah, that's all for the paper. Thanks for watching.